Okay, great.
Yeah.
Thanks for the invite, and it's great to be here. And as I said, I'm Sumith. I'm a third year PhD student at Stanford, and this whole project is joint work with my great set of collaborators, co-led by Jiawan, who is a PhD student at MIT, and my advisors Alex and Jiajin. So it's a paper that was presented at CVPR, and we call it motion programs. So I'll just talk I'll give a brief overview of our framework, and then talk about some of the applications. So let's get right into it. Let's see. Oh. Okay, so current works in video and human motion analysis either work at the pixel level or the key point level. For example, like this video of jumping jacks would most current systems would analyze them by looking at the individual frames or the key point trajectories as shown on the right here. But then there are higher level primitives of motion to these actions. For example, this video of jumping jacks can be looked at as a sequence of two primitive actions, which is moving hands up and bringing them down. And the whole video is just like a repetitive pattern of these two primitive actions appearing alternatively. Similarly, like for squats, it could be looked at as a repetitive pattern of squatting down, standing up, and a brief resting phase while standing. Such primitive level understanding is currently inaccessible to video analysis systems. So to that end, we propose a hierarchical motion understanding framework where we hope to capture such primitive level understanding and higher level relationships. So our first level consists of just key points. At this level, we represent the pose level information that most current systems do. At the second level, we have what we define as concrete motion programs. This level can represent the primitive level information by grouping together a sequence of frames and poses, such as moving hands up for the jumping jacks video. And our third level consists of abstract motion programs. At this level, we represent the higher level information, such as the repetitive pattern of these two primitive actions. And we do this using a for loop structure as shown on the right. And together, these three levels of abstraction present a new way of representing human motion, giving access to higher level structures like primitives and their repetitive structures that were previously not accessible. So now I'll describe the framework in detail. So I'll describe the representation where we represent information in the higher levels of the framework using two simple program like DSLs. And I'll also describe how to synthesize these programs given any input video. So I actually don't see any of you when I'm on the talk. So you can just interrupt me and just unmute yourself and just talk.
Okay, will do.
Okay, great. Okay, going forward. Let's begin with the level 2 with concrete motion programs. So concrete motion programs are basically sequences of primitives where each primitive could either be a circular, linear, or stationary motion. And each body key point has one such program. And each of these primitives have spatial parameters, for example, for defining a circular motion, you have the center, radius, and angular, and all the motion parameters like velocity and so on. So first, let's see how to synthesize one primitive, and then we can also look at how to synthesize a sequence of such primitives. For example, for this jumping jacks motion, looking at the right wrist key point, the right wrist key point traces the trajectory in green as shown on the slide. We first induce the best fit circle that well approximates this input trajectory, along with the appropriate motion parameters such as angular velocity and angular velocity and initial angle and so on. And similarly for for a linear motion, for which is example of which would be the neck key point in the squatting motion, we fit the best fit line along with the appropriate velocity parameters, and this kind of approximates one primitive. But for long videos with different motions, rarely can they be expressed with a single primitive. So we need to synthesize a sequence of such primitives. So for a long video, the goal is to jointly segment the video at the right primitive boundaries while fitting a primitive for each of these segments. And the goal is to like minimize the global error of like jointly doing the segmentation and the primitive fitting. So for that purpose, we define this recurrence relation. And this recurrence relation basically says that the error that you get for the first n frames, for the program, when you fit the program, the error that you get for the first n frames is the error that you get for the first k frames plus the best fit single primitive error from frames k to n, minimized over all possible values of k. And if you solve this recurrence relation, the paper has more details. We use a dynamic programming algorithm with some optimization to actually like scale it for larger videos. You get a sequence of such concrete motion programs. And once you have a sequence of such concrete motion programs, you basically have a representation that approximates the input trajectory with like a program-like representation. So that gives us concrete motion programs. Now, once we have concrete motion programs, we want to synthesize abstract motion programs. Just to recall, abstract motion programs kind of capture the higher level repetitive structures of these primitives and so on. So at this level, the DSL here is might not, all the details here are not important. Basically, there are abstract motion program has a sequence of statements where each statement could either be like a leaf statement or a for loop, and there are like two kinds of leaf statements. So one is like a deterministic primitive, which is basically like a concrete motion primitive, but it has a different representation where it is encoded instead of encoding it as circular, linear, and stationary motion, you encode it using start point, midpoint, and end point. And we do that just so that we have a common representation for all three primitives. And a probabilistic primitive basically tries to capture a distribution of such deterministic primitives. Why we do that will be clear in a bit. So, for example, once you have the concrete motion programs, which has like a sequence of primitives as shown here, we first convert each of these primitives into like this a start, middle, endpoint representation, and the goal is to capture repetitions, right? So how we do that is we search for windows of primitives in the concrete motion programs and try to identify groups of try to identify segments of repetitive motion, where a repetitive motion would be a motion where like if the parameters of the deterministic primitive, such as start, middle, endpoint, are kind of along the same area. So
so can I have a question? Quick question here. When you say we search for, are you describing an algorithm, or is it something that you have actually manually looked at and decided that?
Oh no, yeah, it's like an automatic. It's like automatic algorithm. So we basically search for. For example, the repetitive pattern could be of loops of body size 2 or 3 or 4 and so on, right? So we don't actually like look for them manually. We have an algorithm that kind of does a sliding window. So you take a fixed window of segment, say 20, and you slide it through the program, and you try to search if this window has a loop of body size 2 or body size 3 and so on. And how you actually do the search is you look at the start, middle, end points of each primitives. And if the variance of the start, middle, end points is low, that means it's a repetitive motion. So you kind of mark that as repetitive motion. And for loops of, and when the sliding window like goes through the whole program, you can find like the maximal windows which can be considered as loops. Does that make sense?
Yeah, sure. But then the primitives like circular motions, those you discovered manually, right? You didn't generate this. The fact that you have these three primitives like linear motion and circular motions, that's something that you decided as developers.
Oh, yes. Yeah. So there is like there's a DSL and there is some inductive biases that we have put into it, which is that the motions can be like linear, circular, or stationary. So those are fixed. So the DSL is fixed, but then any inference of like programs from the DSL is automatic. So there is no intervention. So the whole system can run end to end, and given a raw input video, and if you have the detected poses, you can synthesize programs without any intervention.
Okay, yeah, thank you.
Okay, sorry if this slide maybe was a bit unclear, but yeah, basically we like search for windows of like loop of repetitive loop patterns, and we like replace them with a like a probabilistic primitive. So for example, for some intuition here is that the jumping jacks motion, there is a repetitive pattern of two primitives. They appear alternatively, but each of the primitives here, if you're trying to have a compact representation like a for loop and trying to roll these similar primitives into a for loop, the different repetitions of the jumping jacks kind of have the same motion, but not exactly the same motion. So you cannot replace them by like one single primitive. You have to replace them by a distribution of primitive which captures the variance of motion across these different repetitions. So that's why when we roll up repetitive primitives into a for loop, we, instead of having like a single primitive, we kind of have a distribution of primitives. And at execution time, we basically concrete primitives are kind of sampled from the probabilistic primitives. So that gives us the ability to capture repetitive pattern and their like distribution. So once we have once we have the abstract motion synthesized, we like that completes our framework, and together like these three levels of like representation can capture like primitive level information and their higher level relationships such as repetitions. So that completes the representation and the synthesis. So now we can look at some downstream tasks. So for experiments, we run two kinds of experiments. One is to evaluate the representative power of these primitives and of the programs in general, and then the other is to evaluate the benefits of having such representation in downstream tasks such as video interpolation, extrapolation, and so on. So I don't know how the videos kind of render on your end. So this is kind of the representative power experiment. On the left, we have like a golf swing video and the detected poses. And on the right, we have the motion program synthesized for the left wrist key point. And on the far right, we have the program case pose. So this is the key point sequence that was generated by executing the program. So we notice that there is only a minor difference between the input pose trajectory and the synthesized key point, showing that like these programs can do a good job of encoding the input trajectory. So on the whole data set, this video is from the golf DB data set, which has many videos of golf swings. On the full data set, we synthesize motion programs for all the golf swing sequences, and we did some we pulled out some numbers. So comparing the program representation with just the 2D key point representation, we noticed that our representation is efficient, which is that since programs are a more compact representation, programs needed only like 253 parameters per video, which is much lower than like 1,600-ish parameters that you need for representing the pose sequence. And along with being efficient, they're also accurate, where despite this decrease in the number of parameters, the programs differ by the ground truth pose sequence only by like 6.25 pixels, which is just 2.4% error. And they're also more temporally consistent. Since program generated poses, they kind of like approximate like a set of frames as one primitive. They are temporally more smoother than pose sequence, because pose sequences can have noise at times. Okay, so the next application we look at is is video interpolation. So SEPCON is a standard video interpolation baseline which takes the left and right frames to predict the intermediate frame. So the goal is given like a sparse set of frames, generate the intermediate frames to have like kind of a higher frame rate video. So how we incorporate motion programs is, instead of just passing the left and right frames, we pass the left and right skeleton heat maps as well as the intermediate skeleton heat maps, and try to synthesize the intermediate frame. This intermediate skeleton heat map is usually not available at test time, but if you have motion programs, you can have the intermediate skeletons. And just as an ablation, we also just like have a model that just takes the left and right frames and their skeleton heat maps to see what the difference is. So at test time, what we do is SEPCON basically takes the sequence of frames and generates a dense sequence of frames. But what we do is we use the sequence of frames to generate the skeleton heat maps, and then run motion programs to kind of capture the motion and execute the program with a finer granularity of time to generate the intermediate skeleton sequence. And once you have this, then we again generate the output, the interpolated output video.
So I do understand correctly that like this representation, because it's parametric, allows us to like sample the sequence like at any desired frame rate.
Yeah.
Right?
Yeah.
So that's like a good feature to have, right?
Yeah. So yeah, these programs, yeah, you can like sample them at any frame rate. So you can execute, you can execute at t equal to 0.3. So if you have a good representation, you might not have that pose at that time, but you can get it through this program. Yeah. And then for the ablation, we just kind of have the video and the pose, the detected poses, and we try to synthesize the interpolated video. So this is the results on 2x interpolation. We notice that our results are kind of comparable with the SEPCON results. The left is the baseline, right is our model. And this can also be seen by the numbers, where like our model performs kind of equally well with SEPCON, and at times like marginally better. But then for 8x interpolation, where you're trying to predict, like you have the frame number 1 and frame number like 8, and you want to synthesize all the intermediate frames. So you can spot that our video on the right has like retains more higher level structure of the hands and the motion of the hands compared to the baselines. This can also be seen by the error heat map with the ground truth frame, where our model has lesser error at the boundary of the hands than the baseline, and it can also be seen in the numbers, where if you notice the key point difference for the hands key point, like the elbows and the wrist, the key point difference generated is much lower than the baselines.
Okay, so can I clarify something?
Yes.
As I understand, is it like the model, like in this task, you have a video generation model that takes your like poses generated by this symbolic approximation abstract generative program, right? And outputs a video like from still image, like what the visual initialization for the generation task?
Oh yeah, so the initialization is that you just have the left and right frames. Let's see, you have. So I think this is the initialization. So by initialization, I mean, are you asking about what the input is? Because the input is like a sparse set of frames. So if you have a golf swing video, you kind of drop everything except the 8th frame, and you try to reconstruct the full video.
Got it. So it's like super resolution in time. Using like auxiliary information generated by this program.
Yes. So either you can just use the frames to generate, which is what like everybody does. But if it's like a human motion where you can synthesize a decent program, we just show that synthesizing the program kind of gives you like this additional signal that can be used to do the video synthesis better.
So you're saying you ran this on 2 datasets. Is there any difference in the DSL or hyperparameters or anything between 2 datasets?
No, I think there isn't any difference between the hyperparameters or anything that's specifically tuned for these datasets. But you should also know that these 2 datasets are kind of very similar in the sense that the post-warp dataset mostly also has like golf swing videos. We just chose to run it on these datasets, but yeah, because it's like a standard data set which was used in other papers, but you can run it on any video given like sufficient data, I guess.
Yeah, in the article you say that at some point you compare to the Everybody Dance Now again, like as a baseline.
Yeah.
Can you talk more about that?
Oh yeah, that is in the video prediction, which is the next experiment. So we can.
Okay, sorry.
We can get to that in a bit. Okay, so yeah, so the one final set of evaluation metric that we also use for interpolation and also for extrapolation, which I'll talk in a bit, is that we perform human evaluation just to make sure that the quality of the videos generated for our method is kind of actually better than the baseline. So for every interpolation factor and for both the data sets, we recruited 30 30 workers from Amazon Mechanical Turk to kind of evaluate which video looks kind of higher in quality. And it can be seen that our videos are kind of rated higher, and it's rated higher when the task is harder and the interpolation factor is higher. So that is just like, yeah, I kind of just for like to get a sense of the visual quality of the results. So, okay, so another set of experiments that you can do is, I think there is some interest in like detecting and extracting repetitive segments in like a long video. So as we synthesize abstract motion programs, which has a for loop structure that kind of captures the repetitive patterns in videos, you can extract loops from like videos that have, like, for example, for exercise videos where there are a lot of repetitive exercises, you can like detect and extract these repetitive segments from the videos. So we downloaded like 3 long videos from YouTube, which are like in order of like 20+ minutes, and we hand labeled all the repetitive segments in these videos, and we use motion programs to kind of detect these repetitive segments. So it can be seen that with like good precision and recall, we can detect a lot of like the loop structure that is there in the videos. And here are some samples. I mean, there is more in the, maybe if the videos are not rendering properly, there's also like a version of the stock online, so you can look at that. But these are like a few samples of like the detected repetitive motion using the abstract motion programs. So finally, just to talk about the video prediction task that was just raised. So video prediction is a task of, given an input post sequence, try to predict the future post sequence. And this is there's a lot of literature on this, and we use like two very popular baselines. One is hierarchical video prediction model, which uses LSTM to predict, like encode the input sequence and predict the future. Okay. And we use this history repeats itself model, which uses attention to, which is like for longer sequence and for longer horizon predictions, is shown to perform better, which uses attention-based model. And for us, we just use motion programs where we try to synthesize abstract motion programs, and we execute for loops for like longer, for more number of iterations. So we do this for the repetitive segments that were detected. The goal of this experiment is just to show that the baseline models don't capture the higher level, like the repetitive structure of such motions, while being able to capture that structure enables you to do like video prediction better. So this is the result of the first 300 frames predicted. So given an input video, what we do is we try to predict the first 900 frames, and then we analyze them in sets of 300. So we look at the first 300 frames, 300 to 600 frames, and 600 to 900 frames. This is just to get a sense of like the decrease in quality over time. So for the first 300 frames, we you can see that for the videos here, most of the models do all the models kind of do equally well. Even at times the baselines also do slightly better by like predicting smooth future post transitions. So, and this is the result from frame 600 to 900, which is the last set. We noticed that the baselines pretty much have diverged and stopped predicting decent post sequences, while our model still predicts decent post sequence. And this, okay. So this kind of happens because like the for video prediction, the baseline models kind of do extremely well for predicting the first 20 to 30 frames, and then the error kind of compounds because you predict a frame, then you use that to predict the next frame, and so on. So the error compounds. While for us, we just predict like the for loop structure and kind of unroll the for loop for longer. So this graph is showing the key point difference of the predicted post sequence with the ground truth post sequence, and across and the x-axis is where you kind of increase the number of frames synthesized. So as initially for like a very small window, we noticed that the baselines do much better, but for the later frames, the key point difference generated by our model is lower than the baselines. And this is also highlighted by the human evaluation. So we did a similar human evaluation, compared the baselines with the for the three chunks of like 0 to 300, 300 to 600, and 600 to 900 frames, and we noticed that the workers kind of rate our video as higher quality than the baselines. So and
yeah, it's also it seems like reasonable because it's like the diagram that everybody who worked on like motion prediction using like Kalman filters or something seen this like kind of drift. So I'm thinking like we can finish with the form. Let's talk some stuff about it. Like the paper, like I'm trying to like have a big picture here. Like I'm impressed how like it's complicated task, and your advisors and you like found ways to like remove a lot of complexity from the project. You know, like the data sets with like that describes the domain of like repetitive motion really well, and like extracting 2D key points, and like the prior inductive bias, like everything like seems like it should work, and it does. So it's great. Like at any point in the beginning, like have you thought about like, oh, we should have used like 3D key points, or we should have accounted for affordances, or we should have like had like some kind of prior, either physical or like locomotion prior, like any of those ideas like were discussed?
Yeah, I think some of these were definitely discussed. So for 3D key points, I think this was raised by some of the reviewers as well. So all of this kind of works if you, I mean, there's nothing particularly limiting about this. About this framework that it has to work on like 3D key points, like 2D key points. So you can, so if you have the base level modules which can synthesize primitives for 3D motion, then you can the segmentation kind of, you can just use the same algorithm for the for loop synthesis. You can use the same algorithm. So you just need to be able to synthesize primitives in 3D. But then like we were primarily focused on 2D videos where like we're primarily focused on 2D key points where like 2D key points do a good job of encoding the kind of motion that's happening, especially for these excise videos and call string videos. Like the camera angles is kind of they kind of focus the person in such a way that the key points kind of do a good job of representing them. And also trying to do 3D key point detection and then doing motion programs might be a bit challenging because 3D post detection is still not there yet, where it's like perfect. But maybe for like motion capture data, you can synthesize like 3D motion programs, and I think that there can be interesting applications there. So that I think is definitely
like we have Taras with us, and he's a PhD student and in KTH, and his team worked on like locomotion prediction, but using like probabilistic models like Glow, you know, like sequence generating. But their ground truth was this kind of data as well.
Yeah.
Hi Taras. So like have you ever heard of approaches of like using raw locomotion data like in 3D and like model it with primitives?
Not no, I haven't I don't know of any approaches, but maybe if there are, then I'm interested.
Yeah, I was just asking Taras, maybe he heard. Oh, we cannot hear you, sorry. Yeah, some problem. Yeah, anyway, there's actually like a long history. Like the first attempts at modeling motion, like in beginning of 20th century, like Taylorism and like productivity research in Soviet Union as well. Like they created those diagrams that you showed like on slide 2, I think. Yeah. You know, like the like they called them dynamograms or something. You know, like each frame, and you trace like a pose of the person. Yeah. And they try to find like the optimal movements of like hammering metal or something. So yeah. It's interesting that your work is kind of like connecting the old, like the approaches of motion analysis, like throughout the century, like last century, and also like neural networks of some kind. Well, mostly regression, right? Neural networks are only in video generation.
Yes. Yeah. Yeah. I mean, I am unfortunately not aware of those works, but I think we should discuss, and I can also read about them and see.
Yeah, I mean, like, are you interested in like continuing this line of research?
Yeah, I mean, we are. I mean, there are some things that are still to be done here, and we are like discussing a few ideas to improve the framework. Also, maybe like look at more applications of having such motion programs. So yeah, we are kind of looking at both, like kind of improving the framework as and like being able to encode more complex trajectories, as well as like maybe there are some downstream tasks that you can do better. Like you can do some interactive video editing, or you can do like even video extrapolation in a more general setting. So there are some directions that we are currently focusing on. So yeah.
Taras, you wanted to say something?
Okay, the audio is off again.
No, you can't.
Okay.
Yeah, the software will not allow us. Yeah, but continuing this to downstream applications, and what you're thinking, like I'm seeing like the juicy parts, the interesting things that a lot of people want is sometimes like predicting human motion on the streets, you know, like for self-driving and stuff. They want to like model agents and like to have like describe behavior of more complex behavior. You need like to raise level of abstraction. Do you think like what would be like, let's fantasize for a second, like if you could continue this project and improve the abstract program like complexity, like how would it look?
Yeah, so there are a few things. So one is so improving the kind of primitives, which would be as of now we just use a circular linear stationary motion just because for the kind of data excuse me, for the data we consider, they do a good job of encoding encoding the input trajectory, and the accuracy is good. And if you execute the program, it will look very similar to the ground truth keep-on trajectories. But then if you go to some other domains or some like random walking videos in the wild with like a weird camera angle, these primitives might not be enough. But it's very easy to add more primitives to the framework. The lower level, the concrete motion program should have just an extra primitive rule, which kind of describes like a primitive and how to synthesize that primitive, and then it can just fit into the whole framework. And you can add more expressive primitives like spline curves and maybe some other way of like representing primitives that we don't know about. So you just need to be
so like I got that, and I see like a real a dichotomy, a problem with like separate lines of research. Like the motion a lot of times is very repetitive, cyclic. That's why your programs work well. like trying to infer loops, like to describe behavior. And probabilistic models that like model motion completely, they like also always, like a lot of times, output repetitive motions. But like what happens when you like change one abstract program to another, like, because continuous models or like probabilistic models that can take control, some control, they can probably like change their output when you change the like abstract program that controls it. And I'm thinking, what is like, is there any ideas how to use more abstract programs and how interpolate between them to describe like complicated behavior? For example, like somebody runs somewhere, then like stops and then ties his shoelaces.
Yeah. So what I'm kind of understanding from that question is that if there is a sequence of if there is a motion and there is if a person is doing several repetitive actions in sequence, then can you use that to do like kind of motion synthesis better? So I mean, there's definitely like one line of work where I like. So, for example, the current video extrapolation models, right? So, if you want to predict human motion, they kind of use the input sequence and try to predict like just the individual poses one after the other. But even in this whole framework, I feel like we didn't exactly explore that in this paper, but I think there is some room to do that, where instead of predicting individual poses, you kind of try to predict like a sequence of primitives, and then each of these primitives you can execute each of these primitives to get like a larger sequence of motion. So if by predicting individual key points, if you can predict up to 20-30 frames if you can well predict the future primitives, then you can maybe predict for longer. And then if you can also predict future primitives along with their like abstract motion program, as in along with their loops. So after running, if like doing something else is very common, like after in your data set, if you see that this repetitive motion kind of follows this other repetitive motion by a lot, then you can also be able to predict that and basically predict like long horizon like pose like future poses. So
yeah,
maybe in that
makes sense.
Yeah. So
maybe Vadim or Taras have any questions or comments?
I think that you should have, when you did the qualitative comparison, you should have also compared to the real thing, because I suspect it might happen actually that people judge that your prediction, your interpolation of what happened is higher quality than what actually happened. Because it's like how people perceive this stuff. Everything should follow this Platonic system. So it would be really interesting to compare actually what people rate higher and how much higher. Your predictions or the truth.
Oh yeah, so yeah, doing the ground truth with the prediction. Like at least for these, I think I don't know if the quality is that that good. That like at least for like the human evaluate. Like I think in video synthesis and image synthesis, like when you synthesize like the super high quality images, right? So I think that these experiments are people are trying to doing it where they try to give like the ground truth as well as the predictions. But yeah, we didn't do that. I think that's a good idea. Like if you have like really good quality synthesis, you can do it.
Yeah, we have like one last question in the chat probably.
Oh yeah, I cannot see the
You
chat.
partially covered it before, but if you can elaborate a little bit.
Oh wait. Oh, okay, now I can see it. Extended to non-repetitive motion, as in like the video extrapolation model for non-repetitive motion. So, I mean, if you want to synthesize motion programs, you can synthesize for any video, right? As long as that video has like humans and like you can do like 2D, you just run 2D pose detection and you can synthesize programs. And it like the quality of the programs will depend like how you can use those programs will depend on like how good quality how good the programs are that you synthesize. But I think this is yeah, I mean yeah, it kind of like basically the first level so I think the question is, would your system work on a non-repetitive motion? I think the first level of synthesizing concrete motion program just segments the video at the right boundaries and synthesizes a sequence of primitives. So there is no constraint on if this motion is repetitive, non-repetitive, anything like works. So you just given an input video, you have a sequence of primitives. And then on top of this, the abstract motion programs is just like kind of identifying some patterns in these like primitives. So one such pattern is repetition, and you can look at these primitives and identify repetitions and replace those repetitive blocks with a compact for loop. But yeah, I think you can just synthesize programs otherwise as well.
Yeah, like you said that like in the paper, there's like parameter lambda that regularizes like the length of concrete motion. So
Yep.
like during this project, like what was the longest sequence of concrete motions that the model was like able to capture?
Oh, that's a good question. So yeah, so maybe like yeah, I don't know, because we like synthesize programs for like so many videos that like I don't know the absolute max number of like the longest primitive. But
Yeah,
maybe like,
can it be like 10? Can it do 10?
oh yeah, definitely. It will probably like in the order of like 20, 30 or like more than 30 frames, like 30, 35 frames, or maybe more than that, but definitely 30 frames. So I mean, even like squats, right? Like if person is like doing a squat very slowly and they like just reach till down, they probably take like more than a second, which is already like for a 30 FPS video, it's already 30 frames, right? So it is yeah, the primitives can be definitely like 30 or more, like the longest primitives. But if it also depends on the rate of motion. If somebody is doing a very fast motion, then the primitives are switching kind of like they're like doing many primitive motions in a very short time interval. So the primitives are also shorter. But if it's like a slow motion with like less number of like sudden transitions, then I think the primitives can be longer.
Cool. We got it. Thank you.
May I also have a question?
Yes, please. Yeah.
Yep, thank you for the talk. As I saw from examples, your videos were captured from a stable camera, I mean from one point of view. Can your approach be extended to the camera movements, or like for a video captured from a megacentric camera like GoPro when you have these movements? Because as I see, the primitives may not work directly in that scenario, and it should be somehow adapted. So what do you think about it?
Yeah, I think that's also a very good question. So it's I think as of now, all the experiments are like a fixed camera where somebody has set up a camera and is recording themselves like working out, or like sports videos where like the cameras are kind of fixed. With the cameras moving, that could be like a bit of a challenge, because we kind of need like to synthesize primitives. We are kind of using like a global coordinate of joints, right? Otherwise, you kind of have to decouple like the motion of the camera with the motion of the joint, and then be able to synthesize motion primitives. We haven't looked at it in detail as to how to actually do that decoupling, and especially with like sudden transitions of like if there is like camera switching between them like one another, then I think you need a way of kind of capturing the global motion of the joints in the first place, and then be able to synthesize programs. So I don't know. I think it's like something that needs to be like looked at in the future. But I think like one way, like what I'm kind of currently thinking is maybe that we need a way to like kind of decouple these two motions and like be able to get like the global joint motion, and then you can do like primitive fitting and synthesis.
Okay, thank you.
Yeah.
I think we can wrap up. Like, I wanted to say thank you for your time today, and also for releasing the code. Like, because sometimes like the people just like put a link to the empty GitHub repo, and it's not cool in my opinion.
Yeah.
And you have your code there, and like good description, like your README is very nice. Thank you for all that work.
Thanks a lot. Yeah, if you kind of try just like if there is something, I mean, we are kind of, it's in the state of flux where like we are improving the system and there is a released version. So some things are here but not there, and we are constantly trying to push as many things out as possible. But if you have any questions there, just like open a GitHub issue or email me and we can like fix it.
Yeah, so can we like share your email to people who maybe wanna like
sure. Yeah, it's also on my webpage, and the project page is also on my webpage, so you can find me pretty easily. So great, yeah.
Awesome.
Thanks a lot for the invite, and it was a great pleasure to be here.
Yeah, thank you for joining us.
Hope you see you in the future on the offline conference.
Sure. See you soon.
Yeah, everybody have a nice day.